Welcome to this section, Variational Problems Involving Functionals. We have studied maxima and minima of functions. These problems are called variation problems. A variable y is a function of another variable x if corresponding to every value of x over a certain range there is a unique value of y. Similarly, a variable quantity v is a functional depending on a function y of x if to each function y of x in a certain class of functions there is a unique value of v. We express this as v equal to v of y of x. We can define functionals depending on many functions and functionals depending functions of several variables. Let us look at the following examples. Example 1. Length of the curve y equal to y of x connecting the points a, ab and b, c, d on it is given by the functional z. This functional v of y of x depends on y of x which is a function of a single variable x. Example 2. Area of the surface z equal to f of xy is the functional v of z of xy equal to double integral root of 1 plus dou z by dou x all square plus dou z by dou y all square dx dy. Projection: the surface z equal to f of xy on the xy plane. Here the functional v of y of x is depending on the function z of xy which is a function of two variables x and y. In calculus of variations, we examine maxima and minima of such functionals. Several applications of these problems are seen in physics. The law of conservation of momentum, law of conservation of energy, Fermat's principle of optics are examples in which method of calculus of variations is applied. In history, the idea of calculus of variation was originally started with the famous problem of brachistochrone. In this problem, it was required to find the curve joining two points A and B not on a vertical line so that a particle slides from A to B in the short time. The theory of calculus of variation was developed by Euler 1707 to 1783 and he is considered to be the founder of the subject. In calculus of variations, we will consider two types of problems. First one, problems with fixed boundaries, and second one, problems with moving boundaries. Let us first take problems with fixed boundaries. Variational problems with fixed boundaries. Let us first consider some fundamental properties of functionals. Consider a functional v equal to v of y of x. The increment delta y in y of x is given by delta y equal to y of x minus y1 of x, where y of x and y1x are two functions in the domain of v. We say y of x and y equal to y1 of x are close in the sense of zeroth order proximity if modulus of y of x minus y1 of x is small. Similarly, y equal to y of x and y equal to y1 of x are close in the sense of first order proximity if modulus of y dash of x minus y1 dash of x is small. In general, y equal to y of x and y equal to y1 of x are close in the sense of kth order proximity if modulus of y raised to k of x minus y1 raised to k of x is small. Above, figure 1 shows curves close in the zero order proximity and figure 2 shows curves close in first order proximity. A functional v equal to v of y of x is continuous at y equal to y naught of x in the sense of kth order if for every epsilon greater than 0 given there exists delta greater than 0 such that modulus of v of y of x minus v of y naught of x is less than epsilon, then modulus of y of x minus y1 of x is less than delta, modulus of y dash of x minus y1 dash of x is less than delta, etc. modulus of y raised to k of x minus y1 raised to k of x is less than delta. A functional v equal to v of y of x is said to be linear if v of y1 of x plus y2 of x equal to v of y1 of x plus v of y2 of x, and v of k into y of x equal to k into v of y of x, where k is a constant. We now consider the variation of a functional. The increment of a function f of x is delta of f equal to f of x plus delta x minus f of x. This can be represented as delta of f equal to g of x into delta x plus h of x delta x into delta x, where g of x does not involve delta x and h of x delta x tends to 0 as delta x tends to 0. Similarly, the increment delta v of a functional v of y of x is delta v equal to v of y of x plus delta y minus v of y of x. This can be represented as delta v equal to L of y of x delta y plus alpha of y of x delta y maximum of mod delta y, where L of y of x delta y is a functional linear with respect to delta y and alpha of y of x delta y tends to 0 as maximum of modulus of delta y tends to 0. Here L of y of x delta y is called variation of the functional v of y of x denoted by delta v. Thus, variation of a functional v of y of x is the principal part of the increment delta v of the functional which is linear in delta y. Look at some similarities between differential of a function and variation of a functional. Consider y equal to f of x and f of x plus alpha into delta x for fixed values of x and delta x. If alpha equal to 0, we get the initial value f of x, and when alpha equal to 1, we get the increased value f of x plus delta x. We have dou by dou alpha of f of x plus alpha delta x at alpha equal to 0 is f dash of x into delta x, which is equal to d of f of x. So, the differential of a function f of x is equal to dou by dou alpha of f of x plus alpha delta x at alpha equal to 0. If the functional v of y of x has a variation in the sense of principal linear part of the increment, then its increment will be in the form delta v equal to v of y of x plus alpha into delta y minus v of y of x. This can be written as delta v equal to L of y of x alpha delta y plus beta of y of x alpha delta y into alpha of maximum of delta y. The derivative of v of y plus alpha delta y with respect to alpha at alpha equal to 0 is equal to limit delta alpha tends to 0 delta v by delta alpha, which is equal to limit alpha tends to 0 delta v by alpha. Limit alpha tends to 0 L of y of x alpha delta y plus beta of y of x alpha delta y into mod alpha into maximum of mod delta y all divided by alpha equal to limit of L of y of x alpha delta y by alpha plus limit of beta of y of x alpha delta y into alpha of maximum of delta y all divided by alpha, which is equal to L of y of x delta y by alpha plus limit beta of y of x alpha delta y into maximum of delta y, which is equal to L of y delta y, since beta of y of x alpha delta y tends to 0 as alpha tends to 0. Thus, if there is a variation in the sense of principal linear part of the increment, then there is a variation in the sense of derivative with respect to the parameter for the initial value of the parameter. Thus, variation of a functional v of y of x is equal to dou by dou alpha of v of y of x plus alpha delta y at alpha equal to 0, which is equal to L of y delta y, since beta of y of x alpha delta y tends to 0 as alpha tends to 0. Thus, as we have defined the maximum value of a function, we can define maximum value of a functional. The functional v equal to v of y of x attains a maximum on a curve y equal to y1 of x if values of v equal to v of y of x on any curve close to y equal to y1 of x does not exceed v of y1 of x. That is, the increment delta v equal to v of y of x minus v of y1 of x is less than or equal to 0. Similarly, the functional v equal to v of y of x attains a minimum on a curve y equal to y1 of x if the increment delta v equal to v of y of x minus v of y1 of x is greater than or equal to 0. The function y equal to f of x attains a maximum or minimum at a point x equal to a of its domain, then at x equal to a df equal to 0. That is, dou by dou alpha of f of x plus alpha delta x at alpha equal to 0 is equal to 0. We have a similar result for functionals. Theorem: the functional v of y of x attains a maximum or minimum at y equal to y naught of x in the domain of definition of v of y of x, then delta v equal to 0. Proof: for a fixed y naught of x and delta y, v of y naught of x plus alpha delta y is a function of alpha, say phi of alpha. This reaches a maximum or minimum for alpha equal to 0. Hence, dou by dou alpha of v of y naught x plus alpha delta y at alpha equal to 0 is 0. That is, delta v equal to 0. Hence, the proof of the theorem. Module 2, Euler's equation. Euler's equation is an important part in the theory of calculus of variation. It is used to find extrema of functionals of the form v of y of x, which is equal to integral a to b f of xy of x y dash of x dx. We will show that the curve y equal to y of x, which extremizes this functional, satisfies the second order differential equation fy minus d by dx of fy dash equal to 0, which is called Euler's equation. We will now derive Euler's equation. We examine the extremum of the functional v of y of x equal to integral a to b f of x y of x y dash of x dx with the boundary conditions y of a equal to y1, y of b equal to y2, where y1, y2 are prescribed at the fixed boundary points a and b. Let f of x, y, y dash be differentiable thrice and the extremum is attained on the curve y equal to y of x, which is twice differentiable. Let y equal to y bar of x be a curve close to y equal to y of x. Consider a one parameter family of curves y of x alpha equal to y of x plus alpha of y bar of x minus y of x. When alpha equal to 0, y of x alpha equal to y of x, and when alpha equal to 1, y of x alpha equal to y bar of x. Therefore, y of x and y bar of x are members of this family. Delta y equal to y bar of x minus y of x is the variation of the function y of x, and it will be a function of x. Consider the family y equal to y of x alpha, where y of x alpha equal to y of x plus alpha into delta y. When alpha equal to 0, y equal to y of x, which is the curve on which extrema is attained, and when alpha equal to 1, y equal to y bar of x, which is the comparison curve. Therefore, value of the functional v of y of x alpha on the family y equal to y of x alpha is v of y of x alpha, and it is a function of alpha, say phi of alpha. We have to extremize this function phi of alpha for alpha equal to 0. Since when alpha equal to 0, y equal to y of x. Therefore, a necessary condition for the extremum is phi dash of 0 equal to 0. We have phi of alpha equal to integral a to b f of xy of x alpha y dash of x alpha dx. So, phi dash of alpha equal to integral a to b fy dou by dou alpha of y of x alpha plus fy dash dou by dou alpha of y dash of x alpha dx. Here dou by dou alpha of y of x alpha equal to dou by dou alpha of y of x plus alpha into delta y, and dou by dou alpha of y dash of x alpha equal to dou by dou alpha of y dash of x plus alpha into delta y dash. Therefore, phi dash of alpha equal to integral a to b fy x y of x alpha y dash of x alpha delta y plus fy dash of y of x alpha y dash of x alpha delta y dash dx. So, phi dash of 0 equal to integral a to b fy x y of x y dash of x delta y plus fy dash y of x y dash x delta y dash dx. Since phi dash of 0 equal to 0, we have integral a to b fy of x y of x y dash of x delta y plus fy dash of y of x y of x y dash of x delta y dash dx equal to 0. That is integral a to b fy delta y plus fy dash delta y dash dx equal to 0. That is integral a to b fy delta y dx plus integral a to b fy dash delta y dash dx equal to 0. That is integral a to b fy delta y dx plus 0 minus integral a to b d by dx of fy dash delta y dx equal to 0. By using integration by parts, since delta y at x equal to a, which is equal to y bar of x minus y of x, which is equal to y bar of a minus y of a equal to 0, and similarly delta y at b equal to 0, since all curves y equal to y bar of x and y equal to y of x pass through boundary points x equal to a, x equal to b. Therefore, integral a to b fy minus d by dx of fy dash into delta y dx equal to 0. This simplifies further if we apply the following lemma. Fundamental lemma of calculus of variations. If for every continuous function g of x, integral a to b f of x g of x dx equal to 0, where f of x is continuous on closed interval a b, then f of x equal to 0 in closed interval a b. In a neighborhood closed interval z d of p, choose g of x greater than 0 in closed interval z d and g of x equal to 0 outside. Integral a to b f of x g of x dx equal to integral c to d f of x g of x dx greater than 0. But we are given that integral a to b f of x g of x dx equal to 0. So, f of x equal to 0 on closed interval a b. Hence, lemma is proved. Now, consider integral a to b fy minus d by dx of fy dash delta y dx equal to 0. By applying the above lemma, we get fy minus d by dx of fy dash equal to 0. Thus, the curve y equal to y of x, which extremizes the functional v of y of x equal to integral b to b f of x y of x y dash x dx, is a solution of a second order differential equation fy minus d by dx of fy dash equal to 0. This is called Euler's equation, and integral curves of this differential equation are called extremals. Now, we consider some examples. Example 1, find out the curves on which the functional v of y of x equal to integral 0 to pi by 2 y dash square minus y square dx, y of 0 equal to 0, y of pi by 2 equal to 1. Solution. Euler's equation is fy minus d by dx of fy dash equal to 0, minus 2y minus d by dx of 2y dash equal to 0, that is minus 2y minus 2y double dash equal to 0, that is y plus y double dash equal to 0. Solving, we get y equal to a cos x plus b sin x. Y of 0 equal to 0 gives a equal to 0 and y of pi by 2 equal to 1 gives b equal to 1. Therefore, y equal to sin x. So, on the curve y equal to sin x, extremum is attained. Example 2. Test extremum of the functional v of y of x equal to integral 0 to 1 xy plus y square minus 2y square y dash dx. Y of 0 equal to 1, y of 1 equal to 2. Solution. Euler's equation is fy minus d by dx of fy dash equal to 0. Here f equal to xy plus y square minus 2y square into y dash. Substituting in Euler's equation, we get x plus 2y minus 4y y dash minus d by dx of minus 2y square equal to 0. That is x plus 2y minus 4y y dash plus 4y y dash equal to 0. That is x plus 2y equal to 0. That is y equal to minus x by 2. Here it can be seen that the given conditions y of 0 equal to 1, y of 1 equal to 2 are not satisfied. So, the given functional does not have extremum values. Example 3. Find extremals of the length of the curve y equal to y of x. Solution. Here we have to extremize the functional v of y of x equal to integral a to b root of 1 plus y dash square dx. Y of a equal to capital A, y of b equal to capital B. Here f equal to root of 1 plus y dash square. Substituting in Euler's equation, fy minus d by dx of fy dash equal to 0, d by dx of fy dash equal to 0. Fy dash y dash d by dx of y dash equal to 0. That is fy dash y dash y double dash equal to 0. That is y double dash equal to 0, fy dash y dash equal to 0. When y double dash equal to 0, y equal to cx plus d, we have a 2 parameter family of straight lines. If fy dash y dash equal to 0, then y dash equal to k. Therefore, y equal to kx plus q, a 1 parameter family of straight lines included in the above 2 parameter family. Let us summarize what we have discussed so far. Definition of functionals, maximal and minimal values of functionals, derivation of Euler's equation, solution of problems of extrema using Euler's equation. Now, try to answer the following questions. 1. Compare properties of a function and a functional giving at least 4 properties. 2. Give 2 examples of functionals depending of 1. Functions of a single variable, 2. Functions of 2 variables. 3. On what curves can the functional v of y of x equal to integral 0 to 1 y dash square plus 12xy dx, y of 0 equal to 0, y of 1 equal to 1 be extremized. 4. Use Euler's equation to test extremum of the functional v of y of x equal to integral 0 to 1 y square plus x square y dash dx, y of 0 equal to 0, y of 1 equal to a. 5. Find a curve with boundary points whose rotation about the x-axis generates a minimum surface area. Here are some books for your reference. Book 1, Differential Equations and Calculus of Variations by L. Elcoats, MIR Publishers. 2. Calculus of Variation with Applications by A.S. Gupta, Prentice Hall, 1997. 3. Differential Equations with Applications and Historical Notes by G.F. Simmons, Tata McGraw-Hill Education, 2006. Thank you for watching this session. We will meet again with another topic. Until then, goodbye.